Good day to all of you. This is Chemistry Grade 12, Unit 4. The topic we are going to start with today is entropy. The objectives for today's lesson include to understand entropy is a measure of disorder of a system in terms of the random dispersal of molecules and of energy quanta between molecules, and to understand that the entropy of a substance increases with temperature and that entropy increases when you go from a solid to liquid to a gas, and that perfect crystals at 0 Kelvin have zero entropy. In this topic, we will look at thermodynamics and specifically the second law of thermodynamics here, which governs the direction of natural change. We will also have a look at energy or enthalpy changes, which you would have already seen in your AS or grade 11. As you know, energy is an essential part of chemistry. In chemistry, energy determines which reactions can occur or which compounds can even exist. You would have already studied about reactions that absorb or release energy. What is the name given to the reactions that absorb, or what is the name given to the reactions that release energy? Do you remember the terms we use? Right. Reactions that absorb energy from the surroundings are endothermic reactions, and reactions that release energy are called exothermic reactions. These are important terms that you still have to remember from your AS. Talking about things that you have to remember, you should also know these terms. Standard conditions, standard condition of temperature, pressure and concentration, that is. Enthalpy changes and Hess's law cycle. Again, the definitions and calculations will be very important. Drawing of energy level diagrams and enthalpy profile diagrams. And lastly, bond enthalpies and mean bond enthalpies. Definitions and calculations will be very important. So why do things happen in the way they do? For example, have a look at these two pictures here. Why does water evaporate? Or why do green leaves turn red in autumn? Well, part of the answer is related to energy. Every chemical reaction makes use of energy to rearrange the bonding between elements in compounds. So basically, thermodynamics deals with these type of questions. Thermodynamics deals with the laws of heat energy and the transfer of it to other types of energy. You may remember the first law of thermodynamics from your O-levels. Energy cannot be created nor destroyed, but transformed from one form to the other. Do you remember that one? I hope so. Well, the second law states that total entropy always increases in the transformation of energy. It says that the entropy of an isolated system always increases. More simply put, the entropy of the universe, the ultimate isolated system, only increases and never decreases. In other words, we can also say that a chemical reaction tends to go in the direction in which total entropy increases. So you might be wondering, what is total entropy, or what is entropy after all? Let's have a look at what entropy is. For entropy, the symbol used is a capital S, similar to the capital H you would have used to denote enthalpy. And when we talk about entropy changes, we would use delta S, similar to delta H you would have used for enthalpy changes. Entropy can be defined as the random dispersal of molecules and energy quanta between molecules. Quanta can be defined as indivisible units of energy or packets of energy. In more simple terms, you can also say it is the measure of disorder or randomness in a system. Have a look at these two diagrams. How would you describe the two here, the one on the right and the one on the left? How are they different? If you look at the one on the left, you will see it's more neatly packed and arranged, whereas the one on the right is more randomly arranged, which means it will have more disorder and therefore higher entropy as well. The units we use for entropy is joules per Kelvin per mole. Furthermore, entropy also refers to the spreading of energy between the particles in a system or between a system and its surroundings. So you may wonder now what a system or what a surroundings is. Let's have a look at what these terms mean and come back to these definitions once more. So this picture shows you a bit of system and surroundings. System usually refers to the reaction mixture, that is, the species that are taking part in the reaction, which is sort of that glowing fluorescent green mixture that you see on the slide. While the surroundings is everything else there, or rest of the universe if you like. In practice, it means the reaction vessel, like test tube, beaker, or even the air in the laboratory. So, if we come back to the definition, where entropy refers to the energy between particles in a system, that involves the reactants and products. Or between system and surroundings, that refers to the species involved and its surroundings, where the energy has been released or absorbed. In other words, we are relating it to enthalpy changes, which you will see later when we do calculations regarding entropy. We must also know what we mean by disorder in the definition. When we say disorder, we are referring to the arrangement of particles in space. Particles could mean ions, atoms, or even molecules. In addition to the arrangement of particles, we are also referring to the number of ways of distributing energy of the system across all available energy levels. So it sort of measures the number of ways particles can be arranged and number of ways in which energy can be shared between the particles. So when you are defining entropy, you should take care in using the terms. Now let's put our definitions to the test. Right, have a look at these two pictures. You've got one glass with crushed ice and the other liquid water. Which one do you think has more order, or which one do you think has more disorder? What do you think? Well, the crushed ice glass looks less orderly. However, don't be fooled. We are chemistry students. We must explore this at a molecular level. You might remember solids, liquid, gases, and how they are arranged when you did your O levels. For example, solids are neatly packed, closely packed, with particles vibrating at fixed points, while in liquids, particles are less orderly and they are able to move more freely compared to solids. And then gases have particles or molecules which can move most freely, I suppose, and therefore the least ordered as well. So in that way, crushed ice is the one that's more ordered, and the liquid water one is the one that is less ordered or more disordered, in other words. This is because liquids will have more randomness, less order or more disorder, because particles can move about more freely compared to the solid, which means they have more entropy as well. So more randomness, more disorder, therefore more entropy. Alright, now here's another question for you. What do you see here? It's quite obvious, isn't it? Pencils, a ring. What more can you say? If we had said two allotropes of carbon, that's what we are looking for. Yep, it's diamond and graphite. Which one do you think would have more entropy? And why do you think that is? What do you say? If you have said graphite, well done. Yes, graphite will have a higher entropy than diamond. As we know, both are solids. But to answer why the entropy is higher in graphite, we need to look at their arrangement. So we've got the allotropes of carbon, that is graphite and diamond here, and you can also see the molecular arrangement. How are the carbon atoms arranged in these two? As you can see, graphite is ordered in two dimensions and has a greater degree of freedom between the layers, whereas diamond has a three-dimensional lattice structure with more ordered particles, hence less entropy for diamond. So here is another example. What you see here is a gas jar where at the bottom you can see it's bromine gas, and at the top you have air is shown with a cover slip between the two gas jars. So let's say those 5 circles, the blue ones, are the 5 bromine molecules, just for example's sake. What do you think will happen if we remove the cover slip between the two gas jars? What would you see? Something similar to that? Bromine in air diffuses after some time so that the molecules of each gas are spread out evenly throughout both gas jars, and that's the reason why you would see something like that. To understand why this happens, let's explore this example further. So we will take the same example with 5 bromine gas molecules, the blue circles again. Now let's say at any given point in time, these gas particles could be arranged in several different ways. Let's have a look at some ways in which they could be arranged, or some possibilities, in other words. Here you can see under number 1, out of the 5 gas particles, the blue ones that is, 4 are at the bottom and 1 at the top jar. So that's one possible ways in which the molecules have arranged. What could be another possible way? Right. Under number 2, you can see that now 3 are at the bottom and 2 are at the top. Do you see how this is going? This arrangement of particles? What could be another possibility? Something like that. You could have 2 at the bottom and 3 at the top as well. How many different ways of arrangement could you possibly have? What do you think? Do you think you could have more ways than just these 3 ways? And what if we, let's say, increase the number of particles from 5 particles to 6? Would the number of possible ways of arrangements increase? Could you have more ways of arranging the particles? What do you think? These are some questions to consider. Well, if you have more particles, remember, then you would have more movement and more ways of arranging those particles, which means more ways of spreading the energy or heat energy. Thus, it will increase entropy as well. So I hope you were able to figure out what we mean by entropy and the ways of arranging the particles and the different available energy levels as well. Now let's consider a substance that exists in 3 different states and see how we can explain the change in entropy of that substance. I've taken water as an example because it can exist as a solid, liquid and a gas as well. If you look at the entropy values, water in different states have very different entropy values. In fact, water in the gaseous state has an entropy of 188.7 joules per Kelvin per mole, the highest, whereas for the solid state it has got the lowest value. To understand this better, let's have a look at this graph of entropy against temperature. Have a look at this graph here then. In general, you can see that the entropy is increasing as temperature increases. As you know, when temperature increases, particles will start vibrating more or moving more freely, which increases disorder. Now, there are 3 important things you need to understand from this graph. The first is, why is the graph starting at the origin? What does it tell us? Right. It means that at 0 Kelvin, the particles have 0 entropy, which indicates that at 0 Kelvin, the substance is a perfect crystal. A perfect crystal is one in which the internal lattice structure is the same at all times, which means the particles are fixed and not moving in any way, whether it may be vibrations or rotations. In other words, the entropy of a substance can only be 0 at 0 Kelvin or absolute 0, and this assumes a perfectly ordered crystal. Second and third fact is the temperature being constant at melting point and boiling point. Why is that? You probably have studied this already in your O-level chemistry, but let's revisit this again, shall we? Here the temperature remains constant as the energy absorbed by the particles is used to overcome the forces of attraction that holds the particles together. Once this attraction has been weakened, then the temperature starts to rise again. The same applies for the boiling point as well. So as you can see from the graph, entropy increases with change of state from solid to liquid to a gas. This is because as the state changes, the distance between particles increases and consequently disorder increases. I hope you were all able to follow these examples that we have taken to give you an idea about entropy. So to summarize, remember that entropy is a property of matter that is associated with the degree of disorder or degree of randomness of particles and also with the distribution of quanta of energy between the particles. This energy will be spread between species in a reaction, that is within the system, or between the species and its surroundings. And the greater the disorder, the greater the entropy. The symbol for entropy is S and delta S for change in entropy. The units used for entropy is joules per Kelvin per mole, and also remember that entropy increases with change of state from solid to liquid to gas. This is because as the state changes, the distance between particles increases and consequently disorder increases. That's all for today's lesson. For next day's lesson, make sure you have a pen or pencil and a notebook so that you can make short notes and a calculator as well for any calculation purposes. Thank you all for joining. Stay safe and have a good day.